hide thumbnail. Okay, there it goes. Hello, everyone. Welcome to EPC 9148 training. We want to just bring everyone up to speed on the nuances of this new board. And we have both EPC teams and microchip teams available today. So first of all, I want to just highlight the board. You can see the photograph of the board on your right-hand side. It is a multi-level converter, flying capacitor type topology, and it has a peak efficiency at the operating points of 98%. Operating point design is 48 to 19 volts. It is low profile. The tallest component is the large inductor on the right-hand side of the board, is 3.5 millimeters. All other components are thinner than that. And so the design is a total height of only 5 millimeters with the PCB. It operates at a constant switching frequency of 400 kilohertz, and that can be reprogrammed in the controller chip, the microchip DSPIC33CK family, as you see in the bottom right here. There are several control loops programmed into it, but it's not as doesn't have every single fault protection feature programmed to it like the 9153. So this is one of the other reasons why we have to make you aware of some of the limitations as it is today. So we have our classic half-bridge topology, which is a two-level converter. And this converter takes that up one level to a three-level converter with a flying capacitor, and that means there are 4 FETs connected in series. This allows many benefits. Most notably in this topology is the doubling of the switching frequency that the inductor sees. This gives a large reduction in inductance needed for the converter, and so you get the opportunity to really improve the efficiency because the inductance is smaller, therefore the parasitic losses are smaller, and therefore making the converter more efficient. In this converter, we can operate, it was designed to operate up to 60 volts, 60, and we use 40 volt rated devices for Q2, Q3, and Q4, and we use a 100 volt rated device for Q1. This is a question we get a lot, and the reason for that is when you start up the circuit, the flying capacitor is at 0 volts, which means that Q1 will be exposed to the full input voltage. Q1 and Q2 form the switches in the step down mode. Step down for this mode is half the voltage of the input and lower, and they are switched at 180 degrees phase with each other. And then Q1, Q4 form a complementary pair, and Q2 and Q3 form a complementary pair. We'll get into some switching waveforms later on. So when your duty cycle is lower than 0.5 or 50%, then we have the following operation. Q1 and Q2 are operated in a complementary mode. So at the equivalent frequency of 800 kilohertz for the inductor, Q1 will switch, and the next cycle Q2 will switch, followed in the next cycle by Q1 again. Q4, as we stated earlier, is a complementary to Q1, and you can see here with the insertion of dead time, Q4 will be in the opposite phase. The same for Q3, and what you'll notice that is with a duty cycle of 50% or less, Q4 and Q3 can be on at the same time. When you look at the switch node, you assemble the waveforms together, and you will have multiple periods of that, and you can see the frequency has now doubled on the switch node with the corresponding ripple current in the inductor. The other key feature of this converter is, in order to have the switch node be constant in the magnitude here, the capacitor voltage must always be maintained at half the input bus voltage. So if you don't, this will be either higher and lower, and you will see this little step in between, and you know that is no longer in proper control. Here we have the charging cycle from Q1 goes through the flying capacitor through Q3 to the output. Then we have a discharge period which flows through both Q3 and Q4. Then we have the second charging period for the inductor that flows through Q2 and Q4. And then we have again the discharge period through Q3 and Q4. As noted before, the ripple current in the inductor is twice the switching frequency of the FETs. When you have duty cycles greater than 0.5 or 50%, then you have the opposite occurring. In this case, you can have Q1 and Q2 on at the same time, whereas Q3 and Q4 won't be on at the same time at all. You still get the doubling of the frequency and for both the switch node and the ripple current. One word of caution here is that in this mode, it is harder for the cascading bootstrap circuit to provide the correct voltages for the upper FETs because neither of Q4 and Q3 are on at the same time. Therefore, you tend to get a higher drop in the voltage for the Q2 and Q1. Those are areas that you should be aware of when supporting customers. The benefit of the small inductor between a 2-level standard half-bridge buck converter and the 3-level flying capacitor converter is shown in this graph. The normalized inductance is calculated here, and you can see that it peaks out at around 25%. That's a substantial reduction. There's another point that you need to be aware of is when you hit exactly 50%, the inductor doesn't have any ripple current anymore. It essentially becomes a switch capacitor topology. The closer you operate to these ends here with this lower duty cycles or at say 45% duty cycle here, the benefits of the inductor difference is smaller. For our converter, we operate at around 37% duty cycle, and you can see the magnitude of the difference in the inductor becomes very large. That's where the benefit comes in. Here's an overview of the board. We have the gate drivers. We use the standard half-bridge gate drivers with internal bootstrap diode. The drivers we are using can be either the LMG 1205 or the UPI 1966A. For the two bottom FETs, we simply use one gate driver per half-bridge FETs. But for the two upper FETs, we use one of those half-bridge gate drivers for each FET and only use the high side portion of the gate driver. Then we use the synchronous bootstrap topology to do the cascading of the bootstrap capacitors and the voltages. And the reason for that is that each time you go up with a circuit, the voltage drop will become larger. By the time you get to the upper FET, it can be as low as 3 volts if you only rely on the internal diode of the gate driver. With the help of the synchronous bootstrap FET, you can maintain as much as 4.7, 4.6 volts on the upper FET with the topology for the synchronous bootstrap. So you need to be aware of that. This is a very important function on this board. You can see here the two bottom FETs, Q4, Q3 with its complementary gate driver, and then Q2 with its dedicated gate driver, and Q1 with its dedicated gate driver. the synchronous bootstrap circuits are also peppered around the gate drivers. We make use of a digital controller, the Microchip DSPIC33CK family. In this case, we're using the 32102 size, which is the smaller one, and it provides all the controls necessary to keep the flying capacitor voltage balanced. It measures, well, after the current sense, which is also a microchip IC, is used to measure the current in the inductor and is fed back to the controller. The voltages of the capacitors, the input and the output voltage are fed back, and the controller takes care of all those controls. Also on board are housekeeping power supply to provide power for the gate drivers and for the controller. The first portion is a switching topology IC that pulls voltage from the input and makes 5 volts. And then from the 5 volts, we use a small LDO to make the 3.3 volt for the controller IC. The controller IC's PWM outputs are 3.3 volt rated and go directly to the gate drivers, which can handle signals as low as 2.4 volts. So there's no concern there that signals are too small for properly providing input to the gate drivers. The board further has a small programming port in the bottom corner here and can also accommodate a heatsink for cooling using these posts providing the correct height and distance. Information for that is provided in the quick start guide, but does not come standard with this board. Here's the optional heatsink that we show here. You can use M2 screws. The information is provided in the quick start guide, and all you need to do is add a thermal interface material, the information of which is provided in the quick start guide, a small patch of it. It is recommended though that the back of the heatsink be insulated from the rest of the board. You can cut out and it's recommended to do so, the portion that rests on the post, because those posts are grounded, and you do want to have the heatsink grounded as well. But you want to insulate the heatsink, and we just use Kapton tape for that so that it doesn't inadvertently touch any of the exposed capacitors on the circuit, which might have a splint of solder. The total system efficiency when operating from 48 volt to 19 volt is shown here, and the converter is capable of delivering 12.5 amps continuous. Here we have a switching waveform of the switch node. You can see that it is switching at 800 kilohertz and is delivering 12.5 amps of current into the load. This drooping of the voltage is normal, and this is because of the flying capacitor being discharged at that point. There's limitations, physical limitations into how large a capacitance you can make it. In addition, the capacitors, many ceramic capacitors do have a voltage capacitance relationship, and to most people's surprise, typical X7R capacitor or X5R capacitor that's rated for 100 volt will actually decrease by 90% capacitance by the time it reaches 50% of its rated voltage. So that's why you need to be aware of that, and this droop here is normal. Here's a thermal image of the converter that's operating at full power. This converter is very efficient, and it does have approximately 400 LFM of airflow on it at that point. That's because there's no heatsink, and you can see that the FETs are pretty cool at that operating condition. Note how cool the inductor is. Programming is pretty easy. There's information provided in the quick start guide for the special cable to connect to that little header. You'll need to have an adapter made to connect to the standard microchip hardware. This is a little custom, but it's not impossible to make. The signals are clearly marked. If you flip the board over, it will give you from pin 1 all the names of the pins, plus in the schematics on the quick start guide. And the programming header is given here from clockwise from the dot, and if you really want, you can still flip the board over for additional information. The programming unit can either use the ICD, which is now the version 4, or the PIC Kit 4 can be used to program the device. The firmware downloading, Microchip is working on the firmware webpage. I think it's up by now. Andreas can confirm that. The firmware description, we use the CK32 MP102 processor with 100 megahertz single core, and the PWM resolution goes down to 250 picoseconds. For the operating mode, we use the average current mode control by measuring the inductor current. The inductor current provides a voltage reference as it does in a standard buck converter. That voltage reference is then measured against the capacitor voltage, the flying capacitor voltage, and the duty cycles for each branch is then adjusted slightly to maintain capacitor voltage balance. Here's the diagram of the controller. We have the output voltage regulation. We measure the output voltage. It gets digitized against a reference. There's a compensator, and there are details from Microchip on how this works and how to program it and measure that. That provides a current reference for the converter. The current is measured from the output, digitized, and it too goes through a compensator. Same technique is used to determine the parameters for that, and then goes into the PWM generator. What you'll notice is that in the PWM generator, there's a second term that adjusts it, and that's called delta D. This is the delta D that is used to adjust for the flying capacitor voltage balance and has a separate controller shown here. The input voltage is measured, digitized, and divided into two. Again, it has its own power plant compensator and generates this delta D2. The voltage is measured by direct measurement of the capacitor, which is differentially measured and provides a single point of measurement for that is digitized for the capacitor voltage, and that then provides the duty cycle for one of the plants to control the system. The part is sold on DigiKey as a EPC9148. There's a landing page with a link here for EPC website, which will then further click through to the Microchip web page and provide links. They should be up and running by now. And there is an article about this converter in Electronic Specifier with a link available in the slides here. And then, Renee, we need to really update this page here.
I see that.
Before we send it out. So I hope the contacts for Microchip are correct. And for EPC, it will be Andrea Giorgiorino, for Asia, and Mark Gurries. And for Asia will be Henry Q and Marco Palma for Europe.
Me too, Brian.
Oh, Brian, sorry, forgot that you were there. Yes.
No problem.
Okay, I think that we'll update these slides. Those are simple enough to update.
Mm-hmm.
And Andreas, the websites for 9148 are up and running now, right?
Exactly. So they are all available. I don't know how you have implemented this on your website right now. Is it?
Well, let's have a look.
Yes, we have a link. So under design support on the 9148 page, there's a link to Microchip. To your landing page.
Okay, good. So from that landing page, this is where users would find all further information. So this is where they find the links towards the firmware. So maybe we can just...
There it is under support files, Michael, on the last one. Yep.
This one, right?
Yep.
Yeah.
I'm going to just click into a separate tab here, and you'll see that it immediately takes you to the Microchip website.
Mm-hmm. So, and so we have this group of information under the short summary. So when you click on documents and software, then this will lead you to GitHub where they can find the software and download the software, but they can also, yeah. So that's a method in software that you can actually get a copy of that development project on your machine so that you can even kind of participate or directly receive updates. So should we make changes to the software, then they find out what's the latest version and they can synchronize their local version with the most recent one we have just released. So the initial software we are providing comes from Yancey. There are definitely some upgrades we need to make, and this will happen, let's say now after New Year. So in early January, we will update the software, minor bug fixes, a little bit of performance improvements. But the most interesting thing is we will provide a fully blown online documentation of the code. So should any customer really be serious about stepping into this application and look for more detailed documentation of the code, this will be available in latest mid of January.
Does that include documentation for, say, minor changes that they might want to make?
Yes. So the documentation is pretty large. So that's basically a website we set up for that. So it provides a high-level overview to get familiar with the firmware and so how the code is written, so that they get their heads around what to find where. And then so in every software example, we have this one central header file. This is basically one file where you're typing all the physical numbers for input voltages, output voltages, protection thresholds. And then we use Intel macros to basically convert these physical values and quantities into binary values, which are then used by the software to program the right values into the registers and so on. So it's fairly convenient to use if you're not afraid in touching code. And so, but still, when you open this project, you will find something like, I don't know, 60, 70 files, right? And it's a little bit tricky to find the right point where you can make these adjustments. And all of that is covered in that software documentation that it's really easy to find. It tells you exactly in which file, at which line you need to make this adjustment to get this and this output.
What about the cable? Is the cable available for programming?
No, the information for the cable is provided in the Quick Start Guide though.
So Renee, maybe let's take this up in the meeting this afternoon. I think we should build a few sets so that we can support customers and also for the FAEs.
Okay.
Thank you.
I do want to add something before I forget. There are some precautions on the converter. You are allowed to plug it in to a 48 volt supply. You just plug it in and turn it on. It does have a startup sequence for the control, but we do not recommend exceeding 20% load of the rated. So that would be approximately 2.5 amp load at that time. It has been tested now to 50% and will pass, but there is risk to the board if you exceed that. So at this point in time, we just ask the FAEs in support of customers. It is documented in the Quick Start Guide. Do not start the converter with a load attached that's greater than 20%.
So in other words, not a constant current. That's
Yes,
the final current.
If
you start it like a resistive load or something, maybe that would work. What do you think?
Either.
Okay.
Right. So if you do a fixed resistor and you choose a resistor that yields 2.5 amps at 19 volts, then that's okay to start. But if you choose a resistor that will result in 8 amps at 19 volts, that's a no.
It sounds like a normal load condition anyway. You wouldn't probably start into full load as this is as the voltage is coming up on the output?
Yes.
Okay, yeah, that makes sense.
So charging of the capacitors on the output is not a problem?
It's not a problem. That's programmed in. Okay. And there's already, if I'm correct, about 200 microfarad of capacitance on board already on the output. So there's no need to add more, really.
What sets the maximum output current? Is that limited by the inductor? Mostly?
The inductor is rated to just under 16 amps. So at the frequencies and the value that it's designed at, it kind of bumps right up against that at full current. But this converter has been tested to 25 amps load current. But it will not do that. It's not designed to do that continuously. It was part of a larger project where that was a requirement that it will be able to do that for 2 milliseconds. But it is designed to operate continuously at 12.5 amps.
Did you change the inductor to do that high current test? Or
No,
same inductor?
It was the same inductor. It was not allowed to be changed. I'll also point out on the board, there are Kelvin hooks on each side. These hooks actually go Kelvin connection to the input capacitors and the output capacitors, so you can get a very accurate efficiency reading.
If a customer wants to change the inductor, would that be a big ordeal because they'd have to go through and make adjustments to the code also? So it's probably not recommended to do that?
Well, yes, it does have an impact on the code. Changing the inductor is fairly straightforward. It's just a surface mount soldering here, although removing it might be a little tricky because the team has glued it down for obvious reasons.
Right.
But if you do change that, you will have to go through the process, through the microchip process here. You probably will also need to remeasure the control parameters. We use a Bodhi 100 from Omnicron. There is provision on the board for the injection of the signals and the measurement of the signals for both current and voltage. And those will be needed to readjust the control parameters. Andreas, I'm not 100% sure, but I think it uses a 3P3Z compensator in both the voltage and current, but I stand corrected on that.
Yeah, almost. I think for the current loops, it's a type 2.
Yeah.
So that's a pretty straightforward one, but the outer voltage loops, due to the high efficiency, we still see a significant impact of a resonant bump. So this requires another additional pole in 0 to be adjusted. And so loop adjustments are actually the easiest changes you can make to the software, because there's a graphical GUI which helps you to do this. So as soon as you're able to determine where the new poles and zeros are of your LC tank, if you know these numbers, then it's fairly easy to just open a nice GUI with a Bode plot, and then you make your adjustments graphically. You hit a button and it generates the updated control code into the software. So that is really the easiest part. Any other modification to the software would take that you really touch the code, actually. But adjusting the loops is the easy part.
And if I am correct, Andreas, as well, the code is operating at full PWM cycle of 400 kilohertz. So it will sample the voltages and currents and update the PWM at a full 400 kilohertz cycle.
Yes, exactly.
So that's the power of this digital controller. I just want to make the EPC team aware of that.
And so as we learned yesterday from the webinar, it's also, I think we had 2 or 3 questions on the flying capacitor voltage balancing. And that is something that would be extremely hard to almost impossible in analog to do it that precisely as we do it in digital. And so during a cycle, so you have that time base of the PWM with a resolution of 250 picoseconds. So you can position an ADC trigger at a very precise point within your signal waveform. And as the device is also generating the switching signal, it's possible to place triggers at exactly the peak values of the voltage, but also we can trigger the ADC twice to sample the midpoint of this doubled current ripple. So even if we are just switching at 400 kilohertz, we are actually monitoring what's going on with a frequency of 800 kilohertz. And that deviation we find between peak and valley of the voltage across the flying capacitor, as well as the deviation between the midpoints between two cycles, gives us an indication how balanced that voltage really is. And this makes this whole control system quite powerful and very stable and reliable.
So Andreas, one of the things for me is for the FAE community to be able to support this board, we would really need a little bit better understanding of this code and the tools that you offer. Could you organize for us a little bit of training on these topics for us? I think it will be very difficult for us to be able to support these boards in the field.
At any time. So whenever you would be available, I would be glad to do this.
Whenever I think we're all here. I mean, except maybe in the next 2 weeks, some people are off. But if you could have the equivalent, presentation that we did today on the hardware, but on the software side, and definitely I'll have my FAEs attend, and I think it will be very useful for us to be able to at least answer the first level of question. Now, of course, we'll send them to you, but I think we need to be able to, speak intelligently about what's going on, right?
Yes, and so we can do this in two ways. We can I don't know how far you would like to dive into this topic. So it can develop in
a rabbit hole. I think I can imagine.
Yeah, quite an ugly can of worms.
But I think, for example, what you mentioned before, having a good overview of changing and tuning the parameters with the graphic tool and how to go through that process, I think that would be a first level support that would be very good for us to be able to do, right? For example, if a customer wants to change their inductor, well, hey, download this tool and this is how you do it. And if we could guide them through that part, would be very good. Okay. The more detail inside the code changes, yes, I think that will be a little bit harder for us. Maybe just an overview is okay.
Yes, and at this point, it might be important to mention that we have established a support network for you guys. So if you send your requests to any of the three guys that you just have seen on the slide, so Stefan, Edward, or Greg, they can forward. So most of the questions, they should be able to answer most of the questions right away. But we have now one person in our apps groups, which is assigned with the task in supporting customers when it's getting into the most minute details of the software. So so she and I will work on any support case that might come in, and then we can.
So the person, the detailed person is which one? Sorry.
So that is we call them SMEs, subject matter experts, and this is a part of the apps group. So every solution we're releasing, they get a really specific in-depth training. They have the boards on the bench, so in case they need to make modifications for customers, they can also try them. So that is Christine on the Philippines. She's not on the list yet, because she should only be pulled in if it's getting tough.
She's a second level. Okay, second level
exactly.
Support, basically. Okay, got it.
Exactly. So the frontline guys are definitely the best point of contact if you have any questions. And if they are not able to answer, and I think this is really only the case when it's going into the depth of the control system, they will just forward this request to Christine, and then Christine will engage with whoever customer directly and solve the problems and work with them.
Go ahead,
Michael. So so back to the training, I would propose we make maybe a 1 hour session.
Perfect.
Just go over the details and introduce you to the tools. should you require more information? So I think most of these discussions pretty soon will go to a level where customers try to understand what the capabilities of such a part actually are. And that would require maybe a second session. So that we look a little bit more on the device, PWM and ADC and how everything comes together.
I mean, we have more and more boards using microchips. So I think, eventually we'll have to get a little bit better understanding. But, I definitely like it. Let's start with 1 hour. At least people have the first, level of answers. And definitely we will leverage as much as we can your support team for sure.
Well, what I would suggest is that, particularly in the beginning, that both members of EPC and Microchip team would be supporting together. That way they cross-educate each other.
Mm-hmm.
Yeah, I think that's definitely, we should do that as much as possible, yes.
Yeah. I'd like to bring up one more part on this converter. It is a little ticker, and it can blow up in your face. And it's
Literally?
yes, and it's an academic issue with the converter. And it only came up because we were using the controller here, and I'll give a brief description of it. So you might have a customer who, for whatever reason, will go at it on their own. And we found this very painful, in a very painful manner. The digital controller has 2 ways of doing its PWM. And I'll just do a single one here. One is called leading edge PWM, and the other one is called falling edge PWM. And in this design, you had to specifically choose to do falling edge for the switches Q1 and Q2. If you do not do that, you'll get in your transfer function, you'll see that as a function of current, so your load current, your I load, increases, the transfer function will start to increase, and then all of a sudden, with a very rapid succession, it decreases. And your phase will go from for example, a negative phase, it will immediately go to a positive phase. And we have, it is academic, and we don't have a full explanation for that, but we do recommend that when you set up the PWM generators, they have been set up for you, is to avoid using the leading edge for Q1 and Q2.
Is this captured in some documentation somewhere?
No.
we should probably capture it somewhere.
That's why I'm capturing it right now.
No, it's good. This is very good, but it's a very,
maybe a comment in the code.
Seems like a very important thing to know.
It is. You'll know when the customer comes complaining to you. That's why I'm making you aware of it now, that if you see this transfer function, they start crying to you, that is, just flip it over to this side, because the default setting in the controller is to use the leading edge.
So Andreas, maybe this is also something, I know you're preparing the documentation of the code. This is maybe something we should highlight also there.
Mm-hmm. Yes. I mean, the setup of the device itself is quite tricky for this converter. So that will definitely get a big portion in the documentation as well.
Okay. Okay. Anything else? Wow, everyone's the expert now, isn't it?
I think we don't know enough to ask intelligent questions. Or at least I don't.
Yeah, I'll also make note here that Worth Electronic also partnered with us on this design. So this started as a custom inductor, and for this specific project that we were working on, but they've now released this part for general sale. So very exciting part here because it is very efficient. It's only 1 milliohm series resistance in the winding. It's a very efficient inductor, as you saw.
Are we
from
linked
the
from their website?
I'm
I
not sure.
think so,
I
actually.
think,
I'll
yeah.
double check that, but
Good.
I think they do. Yeah.
Yes, they definitely have a link to our part on their website.
Yes.
Okay, good,
Absolutely, yes.
I have another question. You said there's going to be an update on the code coming in January.
Yes.
If a customer has a board,
Mhm.
how would they get it updated? Would they send, like, for example, send it back to an FAE? We'd have a cable and update it, or?
Yes, this would be, that might be the best option if they don't have programmers available. Or you can just call the next Microchip FAE. So basically everyone could just reprogram the board pretty quickly. I mean, that is definitely a thing we might have to address from the app side. So we do have simplified programmers. So something that could be set up like in tiny boards included in a cable so that we can directly program it. But this is something I think we have to discuss, Michael, at some point, if you can simplify the programming, if this really becomes an issue for customers. I mean, these Microchip programmers, actually you can program the board with even pretty old ones. So if they have, I don't know, 2 generations back, all of these programmers are still working for these devices. And they're pretty common. So I think in many cases, you might just find a company or someone in that company should have something to program the device. So I hope it doesn't become a problem.
How much does it usually cost? It's not expensive, right?
No, the cheapest one is, I think, something like $40.
Okay, yeah. So we would need one of those and the cable though, which is a custom cable. And with that,
yes,
you can program it.
Yes.
To Andrea G's point, I think it would be good for the EPC FAEs to have.
Yeah, we should,
cable.
and also the Microchip FAEs.
Right,
Yeah.
yeah. Because I think a lot of power supply engineers are not too much into programming and probably wouldn't have those things around as much. And it'd be nice just to be able to say, well, just send it to me. I'll update it and send it back to you, and that would maybe make things go smoother.
Yes, and you definitely don't have to send it around the globe. I mean, the next possible Microchip support person should be just around the corner. So, and as I said, every one of them would be able to reprogram board. So the 9148 is really the only board where we used non-common, non-standard programming interfaces. All the other boards actually have standard Microchip programming interfaces so that you don't need any adapter cables or so. That's a particular thing with this board.
Apps will avoid doing that mistake again. Don't worry.
Yeah. Okay.
So the other EPC boards have a standard connector, basically?
Yeah.
Yes. So this is the only EPC board that has that. Okay, well, good to know.
Exactly. Yeah. Okay, so for the 16th bricks, okay, you would need this text fixture. So the text fixture is actually the one that has all the interfaces to program and debug the controller.
The motherboard, yes.
Yeah. Then I don't know, the 53 has it on it, and I think pretty much, no, if I haven't missed anything, but I think all the other boards have standard connectors here.
Yeah. I found that here they have the 9148 on Worth Electronics website here too.
Okay, yeah.
And they're promoting the inductor here, and there's even CAD files for it, LTM, even an IGES step file. So they're pretty. So and it links to an article on how to power that John Jing had written at the time. So they're also pretty well linked.
I wonder why it says LM5165 on the title of that.
That is the housekeeping power supply that's on the board.
Oh, okay.
So if you look on the board,
yeah,
that's the chip here.
Okay.
So, Michael, how's Lang going to be set up for this?
Lang?
For
What do you
production
mean?
of the boards?
He has a special harness that plugs in here and here, and he's got a programming cable, and he's already been programming and testing these boards.
Okay, I didn't know what he was set up for. Okay.
Yeah, no, he's quite capable of doing that. Like I said, we won't make that mistake again. The holes at these are very small. There was a lot of pressure for this board to be as small as possible, and that's why you see it's very compact. But the 9153 is a good example of say, no, we're not going to do that anymore. I can show you the 9153 is.
So for the 9153, you just buy a cable from Microchip to do it, basically?
You can even plug the programmer.
The programmer comes with the cable already. So you just buy the programmer we were talking about before, and then that's it.
There's two programmers that are compatible with it. See this little 5-pin header here, this male header. If you use a PIC Kit 4, that PIC Kit 4's the bulk part of it just plugs right into it. If you use the ICD4, it has an RJ11 cable to cable, and then there's an adapter on the end of it with a female, and that female will plug directly into it.
Okay, so those are the only two kits that will work directly, correct?
Those are the cables that work directly, yes. And you'll notice on this board we opted for the banana jacks, so it made it more standard. So everything's standardized on here.
Great.
And it's the same with the 9143 and the 9151.
So if you have the schematic for the 48, it should be fairly simple to solder an adapter by yourself. So if customers don't want to ship them around, they find all the documentation about which cable needs to go into which pin.
And it's a standard order too, you know. So, but because it's meant to be friendly with the cable.
Is it only 4 lines, I guess?
5.
Okay.
5.
This thing is so annoying.
So that's
yeah. This is the header here, and it should be documented in the Quick Start Guide.
There we go.
Right.
Yeah.
And it uses this cable here and here. And then you use the schematic to identify the connections.
That shows the ICD. It doesn't show the PIC Kit 4. Is that something different looking?
PIC Kit 3 and 4 are similar. They're basically the same. Okay. When we did this, we were still using the 3, and now Microchip has obsoleted it. Some of us are missing it terribly. We wish they would bring it back. Nudge, nudge, wink, wink, say no more. But they just disappeared into the ether, and it's ICD4.
Yeah, so the PIC kits are smaller and more cost effective. So this is really this $40 programmer. This is the smallest thing we have at the moment, and it's working quite well. Yeah, there it is.
And you see the little female header right that plugs right into the board.
Oh, that's the one that plugs in directly.
Yes.
Okay. Yeah. So, by the way, if you're looking for even more cost effective, the snap, so this is this open PCB on the right, that would also work. That's basically the interior of the PIC Kit 4, just without the housing.
$25 housing, I know, it's crazy.
Exactly.
We're in the wrong business.
Andreas, I have a museum piece. I have a PIC Kit 2
Oh, nice. And we're still using them, by the way, because this is
Yes.
the only thing, because it uses a microchip controller internally
Yes.
to program any device. So we can write our own programming code. So when we
Yes.
have new silicon that has no programming directives available yet, then we can write them by ourselves. And this is why all of us still have the Sticky 2, and we
Yes.
keep it,
It's precious. I
safe.
have it in my safe. It's that precious. Yeah.
But by the way, Andreas, maybe also, in the 1 hour training, if you could help us a little bit also to have maybe one slide for our FAEs with this information, I think it's very useful, right? We're not supporting microcontrollers very often. So just to be able to quickly answer the question, okay, just buy this particular thing and have it on even on our standard slides when we talk about these products, this would be very good.
Okay, so I will focus on exclusively on basically handling the boards, handling the micro, and not dive into too many details about the microcontroller itself.
We'll definitely use you guys for the more detailed stuff.
Okay, good.
I have some work for Renee, but I think she can understand what I'm pointing to.
Okay, no problem.
You can do it now.
Yes.
We'll do that.
All right.
Thank you very much.
Okay. Thank you.
Thanks, everybody.
Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Have a good